All right, welcome to chapter 11.1. This is where we're going to start describing motion, especially distance and displacement. So before we can start talking about motion, we need to set up something called a frame of reference. So to describe motion accurately and completely, a frame of reference is necessary. Basically, you want to make sure everyone knows what your point of view is when you are making an observation about motion, because not all points of view will make the same observations. For example, if you've ever been on an airplane, you know that the flight attendants walk back and forth through the plane. If you're on the plane, they don't look like they're moving very fast. They only look like they're moving at maybe 2 meters per second. But from someone on the ground watching that plane go by, they see the flight attendant moving at 2 meters per second and the speed of the plane. So they look like they're moving really, really fast compared to their point of view. This is what we call relative motion, and relative motion is movement measured in relation to a frame of reference. So in the first example, the frame of reference was inside the plane. The flight attendant moves at 2 meters per second. In the second example, the frame of reference was the ground, and the flight attendant was moving like 500 something meters per second because they're moving very, very fast. So when we describe motion, we have to tell people what our frame of reference is. An example is this picture. So if we look at this picture from outside the building, you're like, say what? How did that train get up on the second story before it crashed down to the ground? Like, what kind of madness is this? But if your frame of reference was inside the building, you would see that on the backside of this building is a hill. And the hill is where the tracks leave the building, and then the ground comes down underneath this building here. So the train didn't really crash through the second story. It crashed through the story that the tracks were on, which in the front of the building looks like the second story. So we really need to be clear about what our point of view is when making any kind of observations about motion. Now, once we've established a frame of reference, a number for measurements can be made in any scenario. We can look at how far an object moves, how fast it's going, and how long it takes to get to its destination. And it turns out, for the question of how far is it moving, there are two different measurements we can make. The first measurement is called distance, and this is the length of a path between 2 points. We measure this in things like meters, kilometers, centimeters, and those kinds of things. Displacement is slightly different from distance. Displacement is the straight line distance from the starting point in a specific direction. We also measure displacement in units like meters, kilometers, and centimeters, but displacement has to include a direction. This is what we call a vector. A vector has something, is a number that has magnitude and direction. So an example of the differences between distances and displacement is if I walk from point A to point B. Let's say I'm taking my little dog for a walk in the afternoon. We might walk down one street, over a couple blocks, down another street, and then over to point B. The length of this path right here is the distance that we traveled. But the displacement is going to be the straight line distance from A to B. And you can see that I moved a much shorter displacement than I did a distance. And my displacement wasn't just along this line, it was along this line in this direction. So I moved from A to B, and this is our direction component of displacement. Now another example is this guy, Tim. He's walking to school. And he's walking to school, but there are some bushes in his way. So he has to go around the bushes. So he walks 4 meters to the east, and then 3 meters north, and then 4 plus 3 is 7. That would be his total distance traveled. But his displacement, the straight line distance from his starting point to his ending point, was only 5 meters, and the direction he moved was northeast. So his displacement was 5 meters northeast. His distance was just 7 meters. We don't include a direction when we're talking about distance. Now, if a full trip requires stops or changes in motion, we need to add the displacement from each part of the journey in order to get an overall idea of what's going on. So let's say that as I'm walking my dog, I walk 5 meters and then stop, and then walk 5 meters again in the same direction. My total displacement is 5 plus 5, which is 10. Now on the other hand, if I walk 5 meters and stop because I forgot my keys at home, and I walk backwards 5 meters, my displacement is 0. And this is because we can consider this a negative direction. It's in the opposite direction of what we started in. The other reason is if you think about the displacement as the straight line distance from where you start to where you stop, if I walk 5 meters, stop, and go back to exactly where I started, I didn't really move at all, and so the displacement's going to be 0. And you can see by these two examples how we can add these arrows together that represent our displacement to get an overall displacement. Now, what if I walk 5 meters to the east and then I turn north, like Tim did walking to school? What we have to do there is we have to use the Pythagorean theorem. So you all know this one. It's a squared plus b squared equals c squared. So let's say that a car drives 11 kilometers north and then it turns and goes 11 kilometers east. What we need to do is make a little triangle with these to show the path that was traveled. And this R arrow right here, the red one, is considered our displacement from where we started to where we ended. In order to figure out what R is, we take the first leg of our journey and square it, plus the second leg and square it, and that's equal to this third triangular side squared. So 11 squared plus 11 squared equals r squared. When you do this math out, it's 242. And then when you take the square root of both sides to get your answer, it turns out that r is 15.6 kilometers. And the overall direction is going to be northeast. So the distance traveled here was 22 kilometers, period. The displacement traveled was 15.6 kilometers northeast. So here are the homework questions that go with this video and this chapter. Please have them ready to turn in tomorrow.